Everyone. Today we will talk about an interesting topic which is called tape out. And this is a process where your design goes from one step from your side as a design house, goes to the foundry. And we'll see what all happens there and goes next. So I will try and talk about this topic for about 30 minutes and then I will open up for questions and after which I will proceed further. Okay. I'll try to wrap it up a little early. I want to have a interactive session with people rather than it being a one-way session. So a quick disclaimer, whatever I share here is of my own. There are a few things which are taken from the public domain and rest everything else is my opinion and does not have anything to do with the company that I work with. So again, if there are some academicians here who are interested in engaging with me, either for their training programs or any workshops, they can reach out to me. I present training programs on design thinking, experiential learning, and creative problem solving as part of the curricula and also as extracurricular work. A quick view of the various topics that I have covered with various educational institutions. Typically, I have worked with institutes in entire of Karnataka, some parts of Tamil Nadu like Vellore and Chennai, and some parts of Andhra, where I've also worked with colleges in Hyderabad and Anantapur and Vishakhapatnam. Right. So we see a lot of them here. There was one invitation from a friend and colleague of mine to Srinagar. So that is the one-off activity which happened at NIT Srinagar, the image on the bottom right. One thing which I found was what would be the outcome of all this technical consulting and mentorship that I do with people. So one of the metric I find is how can I ensure that people are getting some benefit. So what I have tried to do in the last 4 5 years, starting to 2020 was write co-author papers with all my mentees based upon what are the work that they are doing along with me, whether it is in the analog domain or it is in the AI or education domain, and ensure that these are the points which are the deliverables from the students. This has been a successful model where a lot of people do their masters or bachelor's final project with me, which ends up to do a group. The group project ends up being a paper which we publish in a very nice conference within India because most of them do not have a permission to travel abroad. There's only one conference which was done, but it was done during COVID. So the sixth item in this list is called C3, which was presented in Germany, but it was an online presentation. Hence, we didn't have to worry about travel. So this is the only conference which was external, right? So So like this, I have tried working with all the other college and student engagements and see how to take them forward. Along with this, as part of the consulting work, I have taken up this activity of teaching, where we offer these courses on Udemy, and you are well versed to take or enroll into these programs and work on them. So for people who are interested to know what I do as part of my projects in the last decade and a half, so say from 2010 onwards, it's almost a decade and a half now. You will see a various ranges of projects, starting with integrated instrumentation circuits for biomedical diagnosis or a lab on a chip application, where another we have is RF testing, analog and integrated circuits. We have high-speed SerDes, which has been my bread and butter job for the last 8 years after my PhD, where I work with 1.25 to 40 Gbps kind of a SerDes circuits. PLLs, right now, currently at Intel, I have been working with a lot of PLLs, especially for the foundry, and we deliver the latest PLL architectures in the latest PLL nodes or latest nodes that is coming out of Intel as part of the foundry offering. I have also worked with a lot of power management and energy harvesting circuits for your benefit on RF to DC conversion or DC-DC conversion, energy harvesting for IoT applications, low dropout oscillators or linear voltage regulators that you have, which is typically used for very high precision analog circuits and etc. Now, before we transition and show you what it is, I really would like to talk to you regarding the transistor story and why tape out is so important. So what I will do is I will quickly share a video with all of you, and from there on, let us go look at some of the latest things that have happened, and then you can use this and see how things come across. So I would first start something with the Intel process technology. This is directly available on the Intel website publicly, and you would see there is something new that is coming out, which is called the ribbon FET. Okay, are you able to listen to the audio in the video that is being shared? Could somebody confirm that?
Sir, can you play the video?
PowerVia will be a first of
Are you able to hear that?
Yeah.
Okay.
its kind backside power delivery scheme that solves one of the biggest issues facing computing today: interconnect bottlenecks. Traditional interconnect technology sits on top of the transistor layer, with all of the power and signal wires integrated. With the new PowerVia design, the power wires are placed underneath the transistor layer on the backside of the wafer. Power is now delivered directly from the package to the transistors through a network of metal layers that are better optimized for this function. Dedicating the bottom side of the wafer to power delivery and the top side to signal routing is simply a better organization of resources. By eliminating the need for power routing on the front side of the wafer, more resources become available to optimize signal routing. The overall result is a significant frequency boost at the IP block level and a reduction in power leakage. The connection to the transistor layer is made through an innovative nano TSV, or through silicon via, which is 500 times smaller than TSVs used in today's most advanced packaging technologies. Intel is again delivering technology that will drive the next era of compute and enable performance gains across a new generation of products.
So let me first pause here and ask, do you people have any questions before I go to the next section on something called packaging, which is really important? Okay. If not, I'll play another video and we'll go from there. This is basically the video which starts right from the first transistor that was built and how
it's often
the technology
said that the transistor is the
from a
greatest
metal
invention of the
planar
20th
MOSFET
century.
to the current
A simple
FinFET
little
technology.
switch. You apply energy to a gate, which turns off or on the current flow through the channel underneath. Electrons flow, and ones and zeros are made. The distance the electrons had to travel was originally how we measured these planar transistors. We made improvements by shortening that distance through shrinking dimensions first. We added new layers that improved control and speed. Different wavelengths of light were used to print smaller and smaller gates, resulting in faster and faster transistors that consumed less space and power. And as these transistors shrank, we were able to fit more and more onto each die. In these early days, we were limited by needing wide insulating gaps in between each transistor. But an innovation allowed us to create trench isolation so the gap could shrink further. By this point, the wires that brought power in and moved signals around had grown from a single layer on top to 6 layers in order to feed all the small transistors. And we switched from aluminum to copper, so they were more conductive. Other new materials were added to further thin the tiny layer above the channel to increase efficiency and reduce leaking energy issues. We also found ways to make the electrons move faster through the silicon channel by straining its crystal structure. perhaps the only time when stress made things go faster and better. A new smaller wavelength light source helped print ever smaller lines, whilst another new material for the channel helped increase transistor speeds. That was soon followed by even more radical material changes. A new insulating material between the conductors, and the replacement of the polysilicon gate material with a combined metal high-K gate structure that was
Please
better
pay
at
attention
limiting
to the graph
costly
on the right
leakage
side,
currents.
where you see the number of
By
transistors.
now, the laser light source wasn't able to print lines any smaller. The features were smaller than the wavelength itself. Water immersion that refracted the light allowed finer-grained printing to continue. A radical innovation was needed to control leakage from the electron channel. This innovation would transform the planar transistor from 2D to 3D, reducing the importance of gate length as a primary metric. In this FinFET design, multiple electron channels emerge from the substrate and the gate wraps around them. This allows for greater control over the current. Transistor node names, long tied to the two-dimensional gate length, now reflect a range of new factors, including smaller features as well as new processes and technologies. We improved upon this new structure so it occupied less space and consumed even less power. But as we continued to shrink, our laser light source reached its limits, even with water immersion. So we had to resort to incredibly complex patterning techniques to fabricate these now minuscule devices. Devices so tiny that they are a mere fraction of the size as compared to when we started this journey. With now more than 19 layers of wires above them, billions upon billions of transistors like these are powering this generation of computing devices. The insatiable demand for ever smaller transistors requires new technological marvels, new printing techniques like extreme ultraviolet lithography, entirely new structures, and new materials are being deployed to meet this need. That's the exciting story of the innovation of the transistor, a story of scale, a story of magic, and a story we're still writing here at Intel.
So there's one more video before I proceed. But before that, I just want to take a couple of questions if you have. I did see a question based on something called, what is a TSV? TSV is called a through silicon via. That means it is a via. Via means a connectivity between 2 points. That is through the entire silicon backend that you will able to connect the front side with the back side. So that is why it's called a through silicon via. I hope I answered that question. Any other questions before we go to the last video? If you would like to ask a question, please unmute and ask the question. I saw Mohan raise his hand. Yeah.
Sir, then between M1 to M2 is also called via, right?
That is called a plane via or a signal via. Through silicon via is through the entire silicon backend.
Okay, thank you, sir.
Yeah. There's a question called, why do we switch to 3D transistors? Can you define what do you mean by 3D transistor here? Because a transistor is always in three-dimensionally. It was two-dimensional planar, and the moment FinFET came, three-dimensional, we went to get a better control of the gate, such that the current control gets better. Ribbon FET unlike MOSFET. Yes, a ribbon FET is basically giving you better gate control, and you have better control on the channel, hence better control on the amount of current flowing through the channel, and hence ability to achieve higher frequencies. Okay, I'll do the next video, and it is after this that the importance of tape in and tape out we will go into. So next we will look at something called the 3D stacking that is being enabled. Okay, so it's a quick look at that video. So after the die is taken out, how do you take the die and then bond it to a chip or bond it to a wafer? This is the process that they show. Wafer mold is a place where you build a molding layer on top of the bonded devices. And then you thin it by grounding it, grinding it, and ensure its thickness becomes really small. Then you go to the reverse of the silicon. You thin down the backside such that the copper can get exposed, and then you start beginning the interconnect plating. And after the interconnect plating is done, you do a solder reflow where the solder bumps are created such that you can flip them and attach. And this is where the Intel specific EMIB connectivity comes in, and where we do the stack attach, where you can stack the devices and attach them onto a singular platform. So the ability to stack them one over the other vertically is one of the best portions of this activity. Okay, and that's it. We will go back to the presentation. Any questions on till now? Okay. Now that you have seen the journey right from say pre 100 nanometers all the way till the very latest ones. Sorry, there was a question.
Yeah, sir. Can you just give an overview of the three videos which we have seen?
I'm sorry, could you repeat it again? You're not audible.
Can you just repeat and give an overview over the three videos which we have seen?
Okay, somehow I am not audible. Could you please come closer to the mic or somewhere? Because I hear, could you give an overview? And after the word overview, I couldn't hear you.
Of the three videos, sir. Overview of the three videos which we have seen now.
Okay, see, basically first, okay, that's very easy. The second video was about the transistor, where you started off the technology, how it scaled, the journey right from the very first transistors to the very latest new transistors that are being discussed in the industry. That was showcased. That was the first video. Second video told you about the first video told you about the power via, which is basically getting all the power connections on the other side of the die, such that from the back side, where the back side has all the power connections and the front side has all the signal connections. So this was the connectivity. And then the later one you got was on the packaging technology, where you spoke about the various packaging methodologies that you follow on the EMIB way. And then, so this is the quick overview of the three videos that we went across. Do you need more detail?
No, sir. Thank you.
So let me tell you why do we need a tape out and what happens by giving you a bigger, more top level understanding of what constitutes the semiconductor ecosystem. Semiconductor ecosystem really needs 5 steps in its process. First thing is design activity, then the wafer fabrication, packaging, testing, sales and distribution. So these are broadly the 5 activities which happen from where you undertake the activity and ensure the silicon products, packaged products are available in the customer's hand. To do that, we have a small grid where we understand what is the ecosystem, and in the current perspective where we are hearing the Indian semiconductor mission or the government of India giving a lot of emphasis on various fabs. Let me educate a few people on a certain intricacies of that. So one is called an integrated device manufacturer called IDM. This player in the industry does all the 5 steps that are needed. Currently, the most common IDMs are Intel and Samsung. Okay, there have been IDMs earlier. For example, TI used to have an IDM earlier. NXP used to be an IDM. Micron used to be an IDM. So there are many IDMs, but they have not scaled down to the latest technologies. They have limited or restricted themselves due to their business needs for their analog processes at higher technology nodes. Next comes the fabless companies. Fabless companies basically do only the design of the work, get and do the sales and distribution of the work. Some of the common design activities would fabless companies would be your Apple, Qualcomm, and Nvidia. So what they do is they do a lot of these things. They also might do some amount of testing, but they do not do bulk testing there. They get the tests done separately. They only deal with the IP sales or the IP distribution later. So they have only two components, design and sales. Third is an IP company. IP company is the one which does sub-modules which are very specific but sell in volume. That makes good sense that they only do the design activity and they build the IP. They would probably test it once as a prototype. Once the prototype is done and it is silicon proven, then they use that to sell it to the various fabless or IDM companies or any other product based companies who utilizes these IPs. They only do the design portion. Then comes the design house. Design house could be people who do both some amount of the activity in the design side and some amount of activity on the mask generation and the wafer fabrication side, but they do not do the rest of it. Very few are come into this nature. And then comes the pure play foundry. The pure play foundry is what they do is they do the wafer fabrication portion and they work with other partners in the ecosystem to ensure that they get the packaging and the testing also done. Okay. Now, if you look at assembly and testing, assembly and testing is only they do the packaging. That means they from the foundry, they get the dice or the wafer. Then that comes into their office. They do the dicing, which is basically cutting the dice. And after cutting the dice, they do the packaging. And after the packaging, they bring out and do the testing. Okay. Now, why is this foundry assembly and testing are all needed? The government of India has started certain initiatives with Assam and Gujarat in nature. And you see them, they are basically doing a fab and they are doing assembly and testing. They are not doing an IDM or they are not doing a fabless, nor they are doing an IP company. So a foundry or a fabrication activity is happening in one plant, probably in Gujarat. Then there is something called an OSAT, outsource assembly and testing facility, that is happening in Assam. That is also happening in some parts of Gujarat also. So if you see, all of these are not in one place. They will all be in different places with different activity. And this forms the semiconductor ecosystem. Now, if you look at what is an IDM, by the logic understanding that we do here, mathematics, a fabless company plus a foundry would end up being what is an IDM. So they will have a bigger scale, bigger scope, and other activity. Now, coming to the title of this talk, right? We said what is a tape out. Now, there are the places where tape in is also being used. So what is the difference? Difference lies in a very simple one. So when you have a fabless company who is doing all the design, and then you have a foundry who's doing the manufacturing. So when a design goes from a fabless to a foundry, right? That is where it happens. Design goes from a fabless to a foundry. Now, the difference comes here. If there is a company A where it contains both the fab, the design house, and the foundry put together, that place, which is typically called an integrated device manufacturing company or an IDM. And another case where you have a company B, which is a fabless company, which does the design and sends it to a company C, which is a pure play foundry. For example, TSMC is a pure play foundry. And company is NVIDIA or Qualcomm, for example. So if you have company A could be your Intel or a Samsung. So these are the examples I'm giving you for each of these companies. So when you probably give your design from your design house into your company, which has a foundry, it's called a tape in. Whereas when you have a fabless company, the design goes outside your company and into a pure play foundry. It's called a tape out. Now, why do we call it a tape or the word tape in? Tape used to be earlier a magnetic disc or a magnetic tape on which this used to run. So for the current generation of people who do not
हाँ
understand
जावेद
tape,
भाई नमस्ते कैसा है
I'm sorry, who's this? Is there a question? Okay. So when you have the tape used to be a magnetic tape, and those people of generation who have not seen a tape recorder through which cassettes used to be placed, imagines for where these cassettes used to be played using music for music in our time, say about 15-20 years back. Magnetic tapes used to be used to take these designs, record their data onto these magnetic tapes, and then send it outwards to the foundry. And the foundry would take these tapes, tape it inside into their device, into their fab and their workshop, get all the designs and done. So that is why the term tape is still kept in tape. Right now, what you would do in your company is you would probably do a GDS2 stream out, and that stream out would become go to a hard disk. You would secure it, and then transfer the data from your design portal to the pure play foundries input portal by a secured communication. You would not have tape in, you just have a digital transfer of data. But tape in used to be there to acknowledge the magnetic tape that used to be present there. So these are the two important things. And I will just give a 2-minute introduction on what are the electronic design automation and the historic perspective and its need right now, just to show how important it is. There has been a time where drawings used to be done on large papers. We used to have jobs called draftsmen who used to draw these on the physical paper, and then that used to go into the design house and they would shrink the design optically. Beyond, and this time you were working at hundreds or probably thousands of transistors. But as the design started to scale, we had to use the computer and the various softwares that came into the picture along with the automation to ensure the scalability of the designs took place, where we went from tens of thousands of designs to a million. And currently we are working in the age where we are doing billions of transistors, and in some cases a couple of billion transistors in a single die or a processor die or a chip. So this is the kind of design complexity that is there. Without the use of tools, it is very, very difficult to do it. And these tools that we use right now are called your EDA tools or electronic design automation tools that are going through. So this has been the core of the growth of electronic design automation in the semiconductor industry. So now before I go to the next set of slides, I'll probably answer a few questions before I go through.
I am hearing about VLSI since 15 years.
Right.
So has the industry not updated to ULSI?
Come again.
From VLSI to ULSI, is this shift expected any in near future?
Okay. So VLSI industry we have been speaking about is a name, but if you look at ULSI, I would give you a time perspective in such a way. VLSI, we were there probably in the 90s. ULSI would be late 90s and early 2000s. So it's already been 2 decades that we have gone way past ULSI in the naming terms, but we have stuck with VLSI because it's just an industry name that we continue to use it. So we are way beyond ULSI also, probably at least 2 decades further. Right? I hope that is fine. Okay, I have a question saying in what ways currently AI is being used with EDA. So there are multiple ways. For example, each of the ADI vendors, EDA vendors that I have listed here. And if you look at the top 3 predominantly in our market, which would be Synopsys, Cadence, and Mentor Graphics, they have brought in various AI methodologies to bring in. First thing they do is how can they remove the regular or the mundane activities that a designer had to do? Can we automate that using an AI tool? Second, there are many verification checks that needs to be done on the engineer side before they sign off. can they also automate that using an AI, such that some of the intelligent activities that human design engineers need to use, can we bring in them and use that? So in the last couple of years, if you have attended some of the trade shows or some of the conferences held by each of these companies, you would have seen the latest innovations that they have brought in, and to see how they can reduce the time to market and enhance the productivity. EDA is always used to enhance productivity and reduce the time to market. The way you can do simulation methodology, or how you can do a testing methodology, how you can do a verification methodology. Most of the time it is to reduce the total time taken, as well as reducing the design cycle time, as well as ensuring most of the mundane regular activity which can happen is tool driven rather than engineer driven, so that the engineer can spend on more critical activities in the design. So this is how AI is coming into the picture in 2024, and we will see a lot more AI in the very near future, in the couple of years, where you would see predominant domination of AI into the verification and simulation methodology, and that will give a lot of space for the human engineers to uh, find new ways, new methods, and intelligent solutions of what they can do. Okay, so Anand says how the semiconductor industry is related to NVIDIA. NVIDIA is a semiconductor company, and it is also one of the companies which builds a lot of chips. And these chips are used in various AI modules, hardware side, where they are running various compute nodes in the GPUs or graphic processor units or various AI processors. So NVIDIA is definitely a part of the semiconductor industry. Uh, Mr. Pathan asked, in which part of VLSI design flow AI can't do the automation? It is probably the circuit design, which is there, probably in the analog and RF circuit design, where AI is yet to get its kind of dominance that is getting in digital and the Verilog flows. That is because there is a lot of intuition and a lot of design knowledge goes into it. You would see that also coming, but not so far. Revant Reddy, it is very funny
What?
that you use Telugu. రైతు బండి ఎవరికి కావాలో వాళ్ళు అప్లికేషన్ పెట్టుకోండి. So see, either keep the question relevant to
Sorry,
it,
my
or
question.
please do not pass comments unless you have a very specific question on that. So if Mr. Revant Reddy is speaking, please go ahead. If not, we can go to the next question.
Yeah. My question is, what is circuit design in VLSI? How is it different from normal PCB design?
Okay, PCB is called that is used to do the external connectivity of the design. Circuit design happens on the ASIC or on the silicon. PCB typically happens on the FR4 boards, where the design within a chip through a package is brought out through the copper conductors onto the other connectivity and work with others. So PCB is the board that you physically see, and circuit design is typically what is there present inside the chip that we do. This is the broad level description, if it is.
Okay, got it.
Yep. Yeah. It would be nice if you can introduce yourself so that we know who's asking and I can address you correctly. Okay. Any questions before we know? Sahwar Khan has a question. Sir, as an electronic engineer, do we also need to learn AI in today's era? I would highly recommend you learn AI, because what is going to happen in the near future is, though your skill set is very good, a person having your skill set plus AI will be the preferred skill set in the future, rather than only having the circuit design knowledge. So at least understand the basics of AI and how to use it and how to leverage it. You do not need to be an extensive user of it. But nevertheless, a little learning on AI does not hinder your progress in any way. It only aid in your career growth.
Sir, I was having one question. Sir, you
Could you
talked
please
about
come really close to the mic? You're really far off. I'm not able to hear you.
Sir, is my voice clear now?
Mohammad Arman. Yes, go ahead.
Yeah. Sir, sir, you talked about GPU, right? Graphical Processing Unit. Sir,
Yes.
what is this and how is it different from CPU?
CPU, typically graphics, if you understand, what is a graphic? Graphic involves multiple streams of data, typically for a video or an image, whereas data is always one stream. Graphics typically use multiple streams. For example, if you have a picture, you have an RGB, 3 sets of colors, multiple combinations of these build. So you later get with the density and the complexity of imaging coming, you have got an 8-bit data, 16-bit data, or 16-bit color processing, a 24-bit true bit color processing. Parallel streams happen. So when you're happening parallel streams of data coming in, you need parallel processing. Graphic processor units enable parallel processing, which allows you to do a lot of activity, engulf a lot of, consume a lot of parallel data coming in, and then operate. CPU typically works on single threads initially, and now they are having multi-threaded operations where a single stream of code is broken down into multiple parallel threads that they can handle. The difference between multi-threaded CPUs and GPUs is getting similar. So instead of handling separate cores in a processor, GPUs use separate processors itself for the parallel processing rather than having independent cores. So the difference between them is getting narrower day by day, but GPUs are expanding their operations by using multiple cores or multiple, I would say, multiple micro process or multiple smaller processors within a large process delivered to you. For example, the NVIDIA has has multiple cores, say probably 100 or 200 cores. Whereas if you're looking at some of the processor companies, you would talk about 20, 30 cores. So 20, 30 cores is great for multi-threading operation, but you are using 100, 200 cores here, smaller number of cores, smaller processing unit capabilities, but a large of them in parallel for the graphics cores. The unit activity that you want to happen in a graphic will be smaller, but more in number. Whereas in a CPU, the unit activity will be much larger and more intense at a higher frequency if possible. So you would see graphic processor units coming up in the sub gigahertz or probably a few gigahertz or above, whereas processors have traditionally already been greater than 3 gigahertz or above. So the rate at which these are happening will happen. So I hope I answered your question, Arman.
Yes, sir. Thank you.
There's a question from Abdur Rahim Jamali. As a third-year BTech student, especially targeting in analog domain, what should be the flow of learning skills to get into the fabs while still learning fundamentals and learning simulating on LTSpice? Could you please suggest some of the possible courses to learn on analog design? There's another question on the similar lines by Vishwateja. What are the jobs in the semiconductor industry and what are the skills required for those jobs? I have a complete slide answering these two, but quickly I'll say, if you are interested to getting into the fabs, then your specialization has to be not electronics. Your specialization has to be chemistry, biochemistry, materials engineering, uh, understanding quantum physics, uh, device modeling, CAD, etc. That will get you into the fab. But if you want to be on the design side, you need to be circuit designers, either on the analog, digital, or the RF front, and in that line. I'll go into the details a little later in the place. Now, let me quickly go back to the what is the tape out flow, and then we will see the job perspective. So the tape out flow happens as follows. So the tape out process began with design closure, then a GDS file generation, which is basically your design file going out. Then before the design file going out, you will do a, okay, It starts with DRC rule checks, which is called your design rule check. This comes from the fab, who tell you what is the smallest gap between the two designs that can be manufactured, and what is the gap between the two smallest metal layers that can be drawn, or vias that can be drawn. So these would come from there. Then comes your layout versus schematic check, where this is a comparison between what you have designed in the schematic versus what is drawn on the layout, and see are there electrical connectivity is correct between the two. This does not understand the functional connectivity. This is only going to do the electrical connectivity. The functional connectivity is done using simulation, which is taken out after the extraction of these electrical connectivity signals. Then comes design for manufacturability, where you talk about design for testing, design for manufacturing, design for others. So it's called the DFX. Then comes the tape out documentation. Once you have got all of these done with the GDS file generated, you generate the tape out document. There's generally a separate team sits to do these two activity, which is a tape out documentation and tape out and handoff, where they access or they have special access with the Foundry, where they upload these details into the Foundry portal, enter the details with the Foundry portal, have a direct sync with the application engineers, and moving forward. Note the keywords portal, application engine, etc. These are the various jobs. I will talk to you at the end of this talk regarding the same. Let me leave out the Swix ones. So these are the jobs that we are looking at. Okay. So now from the designer's end, these are the various jobs that you will see before a tape out happens. There are three streams that you will typically see. One is the digital stream. One is a mixed signal design stream. Third would be analog design stream. Within each of these streams, will have multiple teams. The analog design team will have the circuit design and a circuit validation team, or the RF validation team, then a pre-silicon testing team, then a layout and mask design team made up of multiple people in each team. On the other side, we will have the digital design, which typically works on your RTL or Verilog script writing. Then you will have the digital validation team who will check if all the designs that I've done are according to the specification that is being done. Then once this design is validated and signed off, you will have a physical design team will convert all this RTL to a GDS. This is where you have the physical design or the PD activity happening, or the structural design activity happening. Within this, you will have sign off, STA, timing, etc. Right? These are the various roles that you see in the industry. Mixed signal design team is typically where you see people doing both these activities. This would typically be your system level design people, or people doing ADC and DSC design, high speed analog to digital converters, digital to analog converters. Using them, they will use this in your analog and digital designs respectively. After doing basic designs of these, you will come into the reliability. This is a less spoken in the industry. Not many courses available for this. Not many faculties teaching about this course, but these are some of the most important activity called reliability, quality and reliability, or Q&A. Sorry, Q&R, quality and reliability. In the software side, people call it QA, quality assurance. Here we call it Q&R, quality and reliability. There you are expected to assure a quality of the software quality that comes out. Here you need to show that your device has got high quality and high reliability, and your device will not give up on you for a given number of years, say 5 years or 10 years or more than that. So that is called your ESD and reliability team. Then comes the top level integration team. This top level integration team basically does the integration of all the works of all the other teams done at the top level on the SoC side, ensures that all the top level integration is done. These are the people who typically run the show for these huge microprocessor chips that come out either from Qualcomm or Intel or Nvidia, etc. Reaching this top level integration phase typically takes about 10 to 15 years, in some cases 20 years, before you even understand what this is. You might be doing some top level work in your digital design team or analog design team, but the top level integration for an SoC comes very late in your career. And this is where all your top buck people here sit here, where they have a lot of risk and they have a lot of responsibility. They have a lot of knowledge, and they are here are where all the decision makers typically sit with respect to the technical work. And this is going to be the place where most of the architects, most of the integration engineers sit, and this is where we will you will see some of the most senior most technical people in the ladder of the technical development sit here. Next comes your release of sign-off engineer. This is a person who is closest to the tape out portal from the Foundry, and it is this person who literally calls the shots, saying, are we ready to sign off? are we ready to release the database to them? Because once they send it out, any change that comes back from the foundry will cost you lots of money. We're talking about hundreds of thousands of dollars of money if there are changes happening here. So this person literally, or this team of people, sit here, take the real call of seeing how fast do we release, on how well do we release this database, and at what quality. Sometimes they will take a call to say, if we have to submit the design today, but we are not confident, we will take a small hit, say take one more week or one more month to ensure all the checks are done, because that is a smaller penalty than getting a feedback from the from the foundry and saying we have to do some major change. So the penalty of delaying it by a month sometimes might be about tens of thousands of dollars, whereas the penalty that you would get while getting a design miss would be hundreds of thousands of dollars, sometimes even $1 million. So the amount of responsibility and reliability this team looks into will be huge. And this boundary line that you see is basically the all place where the designers come into place, and majority of the design job roles are on this side. The moment you come onto the other side, you go into the tape out side, and in the tape out side, the amount of VLSI design engineers are lesser. You will see more on modeling engineers. You'll see more on quality engineers, typically masters and PhD only. You will see very less uh, bachelors and masters getting jobs here. So you will see PhDs from physics, chemistry, inorganic chemistry, material chemistry, structural chemistry, crystalline understandings, CAD design, CAD modeling, mathematics people, physics people, tons of people, especially with really specialized degree working on the other side, because they need to extract the best from the performance of the silicon. So I think I will stop here and not go into the EDA, because there are too many things on the EDA side. And I would probably go with questions from people. So I see a lot of questions. I would require Saif Saab to help me moderate and go through all the questions so that I don't miss any. Okay, let me start with this question from Mr. Mudassir. My name is Mudassir. What are the key skills to become an embedded engineer and VLSI engineer? Please roadmap of both fundamentals to get place in MNC companies. Okay. So embedded engineer are people who work on the system level work, where they use ASICs or already pre-programmed ASIC into their work, and then build a prototype using an FPGA and a few other plugs. An example of an application embedded system engineer would be for people who use washing machines. The electronics which is controlling the washing machine is an embedded system engineering, right? So if you need to know what is the timing cycle of a particular product for a wash or a spin, how much time it takes for the water to load, are you working with all the sensors that you have to work with? Are you working with the temperature control if you have? If you have a top load or a bottom load, how much water load can you handle? Understanding the various water pressures in your system, and then integrating a design. This would be the primary uh, outlook that an embedded engineer would work. That is working with multiple sensors, understanding the outcome, understanding the inputs, and going through. A VLSI engineer on the other side will be working on building the protocols for particular chips, for the data paths, for the clock paths, understanding the various methods. For example, if you're working on security, how do you build network security at various stages? How do you build chip security? How do you build programs or networks and hardwire them onto the chip? So each of these has a security aspect. For example, next you can have the protocol aspects, then you can have the advanced design aspects on the processor building side, or the microarchitecture side, or the macro architecture side, etc. So embedded side is more on the physical domain, where you see, touch, feel, and get this work done. You will not see much of these on a VLSI engineer, because most of it is an abstraction driven job, and it is done that way. So if you're looking at an embedded role, is there. Now there is, in between these two, there's a very nice job role which is called firmware. So these are the people who do embedded like job for VLSI products, and they do the talking between the software and the hardware. So they are the firmware people, and that is also an embedded job. So there are core embedded in the in the product or a consumer engineering side. Then there is a firmware person who presents in every VLSI company, product company, which deals with ASIC. So these firmware engineers are the people who write a particular software, for example, in Python, such that they can talk to the hardware present with the hardware interface. So people always assume that there is something magical that happens, that you write a code and a hardware starts working. But the gap or the interface between somebody writing a code, that code getting translated to a language which the hardware understands, and then the hardware description language triggering an act on the hardware, that would be your firmware job, where you can address your memories, you can address your processors and get the action done. So if you are looking for an embedded job in a VLSI company, typically you're looking at a firmware job. If you're looking at a firmware embedded job in a consumer electronics company, you're looking at the job like I described for a washing machine or a refrigerator or a television, or a automotive company like a car where you're building the ADAS system. All that comes into the embedded engineering in the various MNC space. Okay, so this is what you will have to do. It was a very long answer, but had to be done so that I give a clear understanding that. So I hope, Mudassir, you got the answer to your question. ESD. ESD stands for electrostatic discharge. The easiest way for you to all experience electrostatic discharges on a nice windy day. When you touch a metal surface, you get a shock. That is the static charge built up on your body getting discharged on a material or a metal that is connected to a ground, and the current is passing from your body to the same. That is an electrostatic discharge. Now, another example is, if you have ever worn a woolen cloth and somebody brushes your hand along with it and then touches any surface, you either see a micro arc, a small light flash, or a charge there. That is also electrostatic discharge. So when you do ESD, ESD is needed to protect all your device, because the amount of charge that is built up on a human body or a metal or a material anywhere, that can discharge through the metal conductors of your chip and can destroy them. So hence, you will have to protect each of your chip with this ESD and do that. Okay. Then again, Mudassir asked, what are the languages to learn to master in both fields? Easiest way answer is, first learn C, because C is the best language to talk to hardware. After learning C, you could learn probably Python nowadays. It's becoming easier. But apart from that, it is left to your choice to use. These are the two ones that I would always recommend, because these are fundamental and you can learn other languages based on these two. Again, Anand asked a question which was very prominent in the last 20 years, but now people are seeing, what is the need of analog when we are already digital? So the simplest example I'll give you, Anand, if you can hear what I'm speaking right now, that is because of the presence of analog technology, because your ear is analog. It cannot work on ones and zeros. So the speaker output that you're hearing is analog, and the mic that I'm speaking into is analog. The processing, everything happens inside is still digital. So till there is human being present in the world, you will see analog processing happening. And the day human dies off and there are only robots available, everything can continue happening on the digital interface, because robots understand ones and zeros and not analog to digital. But they use analog to digital only when they have to communicate to human beings. If they need to communicate to the machine, they have their own justifying protocols where they can do machine to machine communication. Second, when you're working with artificial intelligence, most of the AI processors still have a better efficiency when they're working with analog. All your extremely low power digital work works on analog. So analog design cannot be taken away in my opinion, cannot be taken away for life, because the most basic digital circuit, for example, a NAND gate or an OR gate, in essence, is still an analog circuit. It works by controlling the voltage and the current passing through it. So, no matter what, analog shall always be present. Okay. Then there's a question from Pathan. He says, can open source EDA tool help student in designing and taping out the designs using open PDKs? Is working in open source EDA tool help in growing in VLSI career? Your first question, yes, open source EDA tools are available and they are being used. There are a plethora of tools available for various simulations. There is Open VLSI, please use them. There is NG-Spice, LT-Spice, Electric, among various other tools which can be used. And you are right now in a state where you can do designs using them. eFabless, which is a consortium of companies who is enabling PDK using the Google Skywater based 130 nanometer 180 nanometer PDK to build these designs and then tape them out. They are available. You can do using open source. Then when you are working with open source EDA tools, it definitely helps, because when you work on open source, you're building them from scratch. So what will happen is, when you have that scratch knowledge, the current big vendors of EDA tools will find your skill set necessary. If not, you can continue to work with the open source community, and you might still get a career boost from their networking and your ability to build great tools on EDA. Okay, the next question is by Pranati. Currently, I'm studying in second year. I don't know whether it's second year B or second year MTech or second year Inter. So I'll just answer assuming it is second year B. What courses do you prefer to do in internships and how to get internships? Please complete all the courses that your college asks you for, because those are the mandatory courses. Anything else is depending upon what is the job market that you're getting. Preferably get into your core skill. Don't work on just getting a job in the market. Ensure that you learn a skill which helps you retain a job in the job market and build your skill based upon that. Okay. Next question from again Abdul Rahim. Are open source EDA tools worth learning, or we should learn industry standard tools which are licensed by colleges? As a design enthusiast or as a designer, I would say you are expected to know both, because the community or the design community is coming in such a way that open source will get a boost, and you would see many companies using only open source than paying a big license fee to most of these companies. So when you work in such a company, which would be a startup, they will not have any industry license tools. You'll have to work with open source. But when you work with companies work with industry license tools, it is better to learn these standard tools that will at least help your skill set be common in the market, and you will at least not be left behind. Next further question from Pranati again. Which is better, front end or back end in VLSI for getting job in future year? See, for example, if you need to build an application, you need both front end and the back end. So you need a job, you need to do both, but you can pick one to excel. So now let us left you that how do you pick one, whether you want to do backend? Yes, pick a backend and excel in it. You can lead to the SoC integration roles. Will be very good. If you're doing front end, then you will do a lot of front end jobs, digital front end, RTL front end verification, digital verification, etc. SoC verification. It's on the other side, you will do analog design, mixed signal design, where you can do all of it. Analog and mixed signal design is one place where the designer is expected to do his own layout also. Whereas in digital, you would see different sets of teams doing. The RTL would be done by one team and backend would be done by another team. So if you want to do stay on the digital side, you can do two streams. If you want to stay on the analog side, it is always recommended that as an instructor, as a company, or as faculty members, If you do your analog and RF design, you are expected to do the layout of that design also. So that will be the best way to reduce the design cycle time. So there's another question. Can we do jobs in VLSI industry after my completing my engineering, or do we have to do masters in a specific subject? For the analog mixed signal industry, most of the companies hire people with a master's or a PhD background. You would rarely see with an undergrad background going into the analog domains. On the digital and verification streams, you would see companies hiring from undergrad spaces. You could upskill yourself while working. There are many uh, postgraduate courses being enabled by some companies. You can definitely leverage them and do that. Mudassar again asks two couple more questions. How to do engineering rather than study the engineering? If you want to do the engineering, you need to first study the engineering, understand how it works, and only then you can do the engineering. If you have a special skill set where you can bypass knowing the theory of engineering and go into practical, I would love to learn from you. And that will be a great thing to learn, because that will solve a lot of job opportunities that now people are not getting, that would get fulfilled. So I would be one of your first students if you can find a way to bypass the theory and do the practical directly. Do let me know when that happens. Thank you. Vishwateja asks, what are the packages there in semiconductor industry? With packages, if you mean monetary packages, I'm not sure. But if you mean electronic system packaging, there are multiple. You would find collad flat package. You find flip chip BGAs, flip chip LGAs, land grid arrays, post grid arrays, CoWAS, and many more other advanced packaging methodology. So I'm not exactly sure what you're referring to though. Going, it looks like some details coming through by the students. Are Razavi Electronics 1 and 2 sufficient to learn VLSI fundamentals? Also, please suggest roadmap to learn design fundamentals. See, the simple roadmap is start with uh, RC designs, then do network analysis where you understand how to do various networks, then understand what are analog communication and digital communication topics. After that, you need to understand what is analog processing. Then VLSI, understand basic circuit designs with op amps, linear op amps. Then understand the control engineering to understand the control work. This would be the basic engineering roadmap. From here, when you want to do your masters, you take up the advanced courses. It could be on the digital stream, on the analog stream, and you can end your roadmap wherever you think the direction which you would like to go to, which is either could be a master's or a doctoral program or a postdoctoral program also in it when you specialize. Okay. Razavi Electronics 1 and 2 are probably good for the basics, but there are a lot more things to know. But if you are able to complete cover to cover what Professor Razavi has been able to do it, I think you are good to go for most of the analog and mixed signal industry. For the digital, you might have to probably even look into Professor Sedra and Smith's work. Ab baat karo. So next set of questions are from Revati. Good afternoon, sir. I am a research scholar. How can I tape out a chip? What are the steps we need to follow? Please give some suggestions, sir. So Revati, there are a lot of steps that can happen. So for example, let me, now would be the time where I would have to tell you. So please pay attention to my presentation. So the presentation would be, you will have to do something called pre-tape-in checks, where you will have to do LVS, DRC, ERC, antenna check, parasitic extraction. Then you begin your signal integrity analysis, power integrity analysis, thermal and reliability analysis. And after that, you do various sign-off tools. For each of these checks, each of these have a various sign-off tools. For the voltage drop analysis, DRC, LVS, post layout simulation, okay, extracted simulation with power, without power, and going through. So there are a lot of steps, but these are just the overview. And typically, there'll be a checklist that the foundry will give you wherever you're trying to tape out. You need to fill each and every of those checklist items there. Then I have a question again from Pathan Rahman. What sets of skills is needed to enter into MNC companies after BE degree, or masters of BTech is necessary? Now, I am assuming you are referring to VLSI MNC companies and not software. If you are software, I'm not sure if I have the full answer. But if you're looking at VLSI, specifically analog, you would need a master's or an MTech in analog design or a VLSI or microelectronics course. Again, similarly, I would recommend having a master's degree in digital communication or digital electronics and verification for a course. Most MNCs rarely hire a bachelor's degree. They would typically hire a bachelor's degree for all the really work intensive digital verification course where they really need a lot of hands to ensure the work is done.
Mr. Javed, I want to interrupt you for now.
Yes, please introduce yourself and then go ahead.
Yeah, my name is Abrar. I'm in IT industry for 15 years. Took a break to join VLSI, but I didn't get enough packages. Okay, but yeah, coming back to this point, the first question is sorry, does Google have any EDA tools? And second question I'll ask straight away. Does VLSI have any collaboration or any competition from the quantum computing?
Okay, first question, let me answer. Google does not have a tool of its own. Google uses the industry relevant tools. Second question, is there a competition from quantum? Definitely it is going to come. But the areas of competition will not be the regular process design and others. This will be something very different, because quantum is yet to reach the stage where they are scaling up on the applications level. And quantum is not very far off from that. So you will see a lot of work happening. For example, coincidentally, I was supposed to attend a quantum course today at IISc. There's a workshop going on. It's called the Learning Seasonal School on Quantum Circuits by IEEE CAS. It was there yesterday and today. Just for this talk, I had to skip the entire workshop so that I can come here. So there are a lot of things being discussed and there are a lot of activities happening. And if your interest is in quantum, I would recommend you start with quantum physics and then proceed to quantum computing and quantum circuits. I hope that answers
Amazing.
your question, Abra. Yeah. Okay. Right. Again, let me continue to the next set of questions. Pushpak, S. Pushpak. His question is, hi, sir. For a BTech engineer, what VLSI field would you suggest? And what textbooks do you think an engineer needs to learn before entering this industry? So, Pushpak, please tell me what nature of BTech have you done so that my answer is more relevant to you? Okay. I'll wait for
She
Pushpak.
says EC.
Let him come back and let's see. Then Raman has a question. I'm a second year electrical BTech student. Is there a way to switch my career towards VLSI? If so, please enlighten. Yes, Raman, there are ways. There are many programs right now in the training market where if you take these courses, typically these would start with the layout courses, analog layout design or the physical design, typically on the layout side. You can begin your career with it. Or the recommended way I would say is finish your bachelor's. In your master's program, you can do a VLSI. I have known multiple people while doing my PhD at Indian Institute of Science who have completed their electrical engineering bachelor's, especially from say colleges like CBIT, Osmania, MJ, and then come and do their master's in VLSI or microelectronics or electronic system design at the Indian Institute of Science and excel in their career by working in these companies. So there are two ways of doing it. One is, like I said, doing a course while doing your bachelor's and entering into the analog or design field, or do a proper master's degree from some of the top institutes in the country and then enter the VLSI industry also. So you could do both. Question is again, I think this is Anand. So Anand says, why don't we get jobs that easily in core companies? And if that, why do they offer less packages? Core companies need core skill sets, and it's not like software engineering jobs where they get a lot of projects to be done. But these core jobs have a multi-year project, and they want people who are very thorough in their core knowledge and have a long-term sustenance in that particular company. So any person who insists on joining a core company, you see their interests are very much in the core, and they are not the people who are typically going behind higher monetary packages. So that is one of the reasons why, as a strategy, you will see a lot of the core companies offering uh, packages much lesser than what software companies offer. Vishwateja again on money, he says, how much LPA will be given to the graduates of BTech in EC to do EC related jobs? That depends upon how good you are. So if you answer good questions in the interview and you are convinced and you can convince the interviewer that you are very good, the package is not substance. But if you are a person who is mediocre and is giving mediocre answers in the interview question, you will get par or subpar packages only, because ECE industries are very specific to the skill set that they are looking for, and they will always pay based upon how good you are. So it is not how much you can get, but how good you are, and that will scale your value proposition much higher. So my recommendation always is to focus on the skill set, focus on your development, the money will follow. Okay, Pushpak answers he's from EC. So Pushpak, if you are already from EC, then it's easier. Just continue to work on your second year and third year courses where you're working on a lot of the VLSI based courses offered from your college. Continue doing that. Ensure you don't study for the marks that you're getting. Ensure you study for the content that is given in that textbook. Consume the textbook on its whole. Do some projects while you're at college, and that should help you grow better in the industry, or at least launch yourself better in the industry. That is what most of the people I would recommend. And if you're trying for an internship, that should be is what you're doing is learn more rather than earn more. Earning will just follow if you really do good. Okay, I see probably the same three people repeatedly asking the same questions based on money, pursuing skills, and manufacturing. Rest, let me take up any question directly from the people, because I literally see the same set of questions getting repeated. What are the funding? What are the fundamentals, resources, better start, jobs, VLSIs? Same set of questions in the questions here in the chat room. I would now take a couple of questions from the open audience.
Again, Abrar here.
Yes.
Can I target for any management roles in the EDA industry?
That depends upon how good is your understanding of the EDA tools that is being built.
Okay, that definitely requires technical knowledge.
Yes. So unless you know what the tool does, when it comes to the product management, may not be. People management should be possible, but even with people management, people like to work with leaders who know what they're going through rather than pure management.
Yeah, I can feel that.
Yeah.
So, Rahman, sir, what colleges do you prefer? I mean, for MTech, for masters, like in MTech, we obviously have IISc Bangalore and some of the top colleges, which are very best for research purposes. But most of the companies are US based, so doing masters in foreign countries and getting a direct entry with no such problems into NVIDIA and some MNCs, big companies. So what do you prefer and what do you suggest us?
So I don't have a set preference. It's like if you get an opportunity to do your masters in India, go ahead. If you get an opportunity to do your masters abroad, please go ahead. Uh, I'm not stopping you or not recommending anything that is not right. But wherever you get it, please go and do a good job of it, and then you will have industry openings accordingly.
Sir, okay. At the least, which college should I prefer? Like for best for technical knowledge, for building up a foundation in the EC jobs.
Okay. For example, see, there is a technology called railway signaling technology. Would you be interested?
Yeah.
Okay. So you will have to work with the signals team of Indian Railways. So if you want to learn that, that is also a very core technology. Now you want to work with how do you establish wireless communication between the aircrafts, both defense and commercial, with an ATC. That is also another technology.
Sir,
How
most
how do you
probably
maintain how do you maintain communication with the underground people in the marines and others? That is also communication technology. So now, can you rephrase your question? What technology you want?
sir, I really want to get into chip designing, VLSI, and like
Yeah.
as you said, framework. In most
Yeah.
probably in the companies like NVIDIA, NXP,
Right.
Texon, and some more like.
Yes. So the easiest answer for this is wherever you can study well and gain more access. Okay.
Yes.
NVIDIA will go to ISC where there are 40 people in a batch, but hire only one or two. Give you an example.
I see.
Okay. So getting an institute does not guarantee a job. How well you learn in that institute and specialize yourself and apply that ensures you something there.
Okay,
Getting
sir.
an industry, getting a college. Yes, go ahead. Tell me.
Sir, according to you, which institute would provide the most technical and the most best knowledge to get into these companies?
That is decided by the placement team because it is the placement officer who goes and fetches those companies for the placement activity. Knowledge wise, you really do not need any institute in the world with the kind of resources available on YouTube today. Frankly, if you really wanted technological knowledge, it's available for free on YouTube by some of the experts in this area here. Literally, the experts, some of the world renowned experts in their area, equivalent to be fellows, IEEE fellows or company fellows, they are putting their material of teaching on YouTube for free. You take, as on today, you really do not need an institute backing you for learning your knowledge. If you really want to get an institute, now that depends upon what specialization you are looking for, because each institute is not blanket and it is determined by the faculty who is going there and each of them offering a particular course for those 2 years where that specialization comes. For example, there are courses in IIT BHU. They are renowned for their RF technology, radars, microwave engineering, right? But how many people even take up those courses today? And these courses are definitely needed in any VLSI industry because they're now working towards 6G and defense. So it's all again dependent on exactly. If you want NVIDIA, the easiest way to search is go to the NVIDIA search job search portal. See which colleges they are willing to hire from. That is the college you'll have to go to.
Yes. Yes.
Okay. Yeah.
Yes, sir. Thank you.
Okay. There's a question from Abdul Rahim again. What are some prerequisites to upgrade my level to write a research papers? I know M. Reza. I have seen his research paper on LDO design. Okay, Munazir worked with me on an internship program for about 6 months, then followed up with another 6 months of my coaching and working on his final year project, and another 3 months on writing a paper. So it took me close to 15 months to mentor and get Munazir to a level where he was able to write a research paper on LDO design. So if you need to work with Munazir Reza and you are from Aligarh Muslim University ZHCET, please reach out to Professor Syed Atikur Rahman or Professor Naushad. They will give you the next steps to be followed from there. Okay, yeah. I think we are 30 minutes past our time. We have crossed the 90-minute mark, and I still see people asking questions. Please go ahead if you have.
Or maybe, Javed bhai, people can connect with you on LinkedIn and you can take offline. Is that okay?
That should be fine. I think 90 minutes is a lot of time for people to stitch on with, but
No,
thank you.
I'm more concerned about your time.
No, today I was in a flow. I really liked the kind of questions people were asking, so I could go ahead. But yeah, I'll still take about last 1 or 2 questions before we close the session for today.
Yeah. So to the audience, Mr. Javed's LinkedIn profile is shared in the flyer. You can connect with him and follow him also for good learning materials, and also connect with him individually to help you with this domain and the career opportunities also. So any last question?
Sir, where did you share the LinkedIn profile? I mean, can you just repeat that?
Javed, in the chat box, can you write your LinkedIn
Yes,
link?
I will add it right away.
Yeah. So again, a request to all the audience, you can connect with him, but please don't disturb him too much, because he's an extremely busy person and very valuable to us. So I would like that people ask only very genuine and important things to Dr. Javed. Otherwise, it will be difficult for him to reply to all the small questions. So please honor his time, his expertise, and whatever you cannot get directly from some websites or some web search, only those genuine questions, please ask to him.
Okay, for a few people who are interested in learning little advanced courses, I offer about 8 courses on Udemy. So you are most welcome to join that program. And let me quickly share my screen. So if you go to Udemy and search Dr. GS Javed, you will see a list of courses that I have. I have typically about 11 courses now, both on basics of CMOS, IC design, op-amp design, till some of the advanced courses on capacitive sensing, ADC design, practical op-amp or circuit design analysis, ring VCO for PLL and DLL applications, high-speed serial links, and LDO circuit design and approach. I think there's one more course. And this is a very recent course that I'm still populating on, called Analog Design Interviews and EC Gate Questions Solved. So Alhamdulillah, I think I'll be hitting my 1,000 enrolled students nearly soon. I'm at 999 as on today. And hopefully that happens and I get to see some of these students doing really well. And I will probably enjoy that in the near future if I see getting a lot of these people. So along with that, for people who are even more interested, if you go to YouTube and put the same Dr. GS Javed there, you will get my channel where I have spoken only about anything and everything related to VLSI in this channel. So all the videos, all the podcasts, all the playlists will take you through the various VLSI based ones. So to make it easier, I have created various playlists where you can go across and ask. For example, you want to do a work in VLSI, or you want to do a PhD in VLSI. Here are a few set of videos that are available. You can go look at them. If you are learning about what are all the various courses available in analog design, there is a nice podcast with about 32 episodes. Please listen to them. Most of the questions that were asked today have been answered there. You can have a look at them. Then there is a full-fledged one semester course on CMOS analog IC design. So for people who really want to study that, can go through. Then 2 years back, I taught a full semester course on CMOS analog IC design in SRM AP University. So the same 19 videos semester course are again done here. The only two videos missing are the project videos, which are kind of hidden, but they are also available. So you'll have the full set of courses going on here. Then there are a big set of courses on working. If you plan to work on a project on RF energy harvesting for any IoT applications or others, you can visit this set of videos. Most of these are based upon a few projects that I've done along with my mentees, and their published papers, works are all here. So you can start off, and if you really like to work with me, we can work on them. Then there are another set of very recent set of videos I've curated based on analog design and testing. How important is testing of analog design circuits? How do you do it? What are the importances? What are the benefits? You will all come here. You can learn more about analog design testing and methodologies here. So good set of videos there. If people are more interested and want to further understand what to look for, then please do visit this particular site called King Consultants Education, where there is another another channel where I talk about apart from VLSI, what are the various other things that are available. I speak about, for example, there is a topic on overthinking in midlife professional career. How do you work with that? What are the things coming up there? Then I talk about research methodology. How do you do advance yourself in research? How do you master? I did a master class on interview skills. What are the various questions that we can do and work? You have those available. Then you have a complete podcast available on VLSI training and upskilling. So you definitely can have a look at them. Then there is a channel on Dr. Javed's VLSI career guidance where the questions, snippets, most of these were curated from the questions that I received on Instagram. How do these topics come into the picture? I have created this, and you can have a look at it also. Then there's a list on all the microelectronics and VLSI. A lot of people asked what are the important microelectronics and VLSI topics. So they're all curated here. Let me give you a full example here. If you look at the big list, you will see a large list of topics starting from RF energy harvesting, capacitive sensing, CTLE, high-speed SerDes, VCO, serial links, IoT, high-speed serial link quick tutorials. What are the various equalization, LDO, a couple of presentations from my conference presentations in VLSID 2020 or IEEE SOCC 2022. My invited talk at IAC on high-speed parallel transceiver. All these material is available for you to go through. There is a very large 20 video check for people who are doing their masters, and where there is one mandatory course called research methodology. Professor C.R. Kothari's textbook is there. Most of that is quickly jotted down into quickly 20 videos, and you can easily write your exam based upon that understanding. So like this, I have tried to contribute or collect information for VLSI guidance in most of these places. So please find time to utilize them and make use of it. Thank you. Sahur Khan asks, have you taught EDA tools course in Udemy? No, I have not, because most of the EDA tool content is proprietary. I cannot use them to create a course tool. But yes, you can just learn about it online. Plenty of videos available.
Okay, Dr. Javed, Jazakumullah khair. Very nice.
Thank you. Thank you for inviting me. And I thank you for the audience for staying for over 100 minutes today. So it's been it's kind of a record to see at least more than 35 people staying for 100 minutes at a stretch. So thank you, Saif Saab, for getting a great audience like this.
Thanks, everyone. With this, we close this session.